Five, 4, 3, 2, 1.
Hello, thank you for having me today.
It's a pleasure to have you. Where do we start? I mean, I was thinking maybe for people who aren't physicists, who don't know much about Einstein.
Who's that guy?
That guy, German guy, Austrian.
Is he Austrian?
Yeah, he came up with some important theories. Maybe you should sort of tell us a bit about what drew you to Einstein's work, and sort of what are the sort of problems that have been left that you felt the need to investigate and find your own explanations for.
Sure. A lot of people have been asking that, and that's triggered something in me to write a second book. The second book wouldn't have been worthy of writing had I not written this book. So it's really a prequel, and it's going to be about that question, how I got into this, my life story concerning this. And the only reason that I would write that kind of a book was because of what's in this book. What's in this book is vitally important and is huge. So how I got into it? Well, basically as a child, around 10 years old, I was going to catechism classes, and the nun that was teaching the class wanted us to find a saint born on our birthday. So I went home, I tried to find a saint born on my birthday, March 14th. And there was no saint born, and there was no internet. So there was, not any searches I could do really at the time. Research was much more difficult in that day and age, 1965. So I just asked my parents, they didn't know anything. And then I looked at the calendar, I saw Albert Einstein was born on my birthday. And that started it, because I went right to the Encyclopedia Britannica and started reading. And I was very impressed by the man and his work, especially the unified field theory, which then I believe I read an article, I believe it was actually by James Clerk Maxwell, but I'm going back a lot of years now. And I was surprised to see that in the encyclopedia. But when I read about that theory, the unified field theory, I thought that was the best idea that I've ever heard. And from that point on, I was just into science, all kinds of science, and especially physics and astrophysics, which then eventually got me into UFOs and studying how they work. That was the main interest I had in reading UFO books. I wanted to know how anti-gravity worked, because I figured they're an advanced species. They've already learned how to conquer the unified field theory, and anti-gravity had something to do with the unified field theory. And sure enough, it was correct. It was a correct assumption. So that's how I got into it.
So what is the unified field theory?
Well, quite simply, in a single line, it's basically the Einstein version, not the quantum mechanics version, which is extremely complex, complicated, and nonsensical. But the Einstein version is, and basically what Maxwell and Lorentz and a lot of the other people were interested in, is electromagnetism and gravity emerge as aspects of a single fundamental field. So the first question is probably popping in your head is, what is the fundamental field? Well, back in that day, it was called the ether. And what is the ether? The ether was basically, they had to determine after a couple of centuries of debate, turns out to be a quasi-elastic solid. And so for the people who are wondering, well, what does that mean exactly? Well, quasi means if you stretch this thing, it snaps back when you remove the force that's causing it to stretch or bend. Elastic means it can be bent. And solid, this is a very important definition. In this case, it means something that is continuous, not something that is impenetrable. There's some material out there in outer space that is a continuous material. It is not made up of parts. It is one continuous solid material.
So the unified field theory is looking at gravitational fields and electromagnetic fields. How do we make these things? How do these things interact? That's sort of that's what Einstein was working on.
Exactly. The electromagnetic field in that time and gravity just seemed to be in different worlds. They needed to be brought together. You needed to find the cause of gravity. Electromagnetism was very well defined by James Clerk Maxwell. One of your boys over there did a hell of a job. Great scientist, one of my all-time favorites. And he's featured along with Einstein, and Michael Faraday also was a guiding light in my work. Maxwell and Faraday made tremendous gains in the understanding of the ether and pushing that model forward. So what I did was I deconstructed that sentence, electromagnetism and gravity, and I turned it back into three primary forces: the electrostatic field, the magnetic field, and the gravitational field. What these amount to, in reality, what they are is three different types of the bending of that continuous material, the ether. So then I worked forward from that and realized that electromagnetism really only comes about because the primary field, which is the electrostatic field, is nothing more than a vortex, a twist of space, a torsion. And because it is constructed in that way, it has a property, it develops a property, a very important property, which is the property of motion. Which I discovered, and I called this discovery the Slipwave. And it's the cause of particle motion. And it's something that Einstein saw in his last days. He was looking for the cause of particle motion. I was able to work out that model, and that will be another research paper at some point I'll have to write, hopefully with the help of some physicists, because I think that can be resolved. But basically, the unified field theory is really all about the electrostatic field, the magnetic field that happens as a result of the electrostatic field, the charge, the Coulomb force in motion. Since it's a twist of space, when it moves, like an electron now, when it moves, the space spins, it's a torsion field that develops as this thing is moving and twisting around the charge. That becomes the magnetic field. The magnetic field only happens when a charge moves. And that's the link between moving electrostatic charge and magnetic charge. And that's what James Clerk Maxwell clearly defined and his electromagnetism. So now we're already 2/3 of the way to solving the problem, thanks to Maxwell. Then it was left up to Einstein and Lorentz and some others to work out the final merging to gravity, which I did in my book, in which I spent quite a few chapters pounding away the evidence, determining that even gravity is another bending of space. And the final field to be understood was how electromagnetic fields in motion, let's say quarks inside of the neutron and proton, create the gravitational field. And I'm just completing the paper now that proves beyond a shadow of a doubt, using equations that are almost 300 years old, that that's exactly how mass is created.
Right, that's what I was going to ask. So as far as I understand from GCSE physics about 20 years ago, that, yeah, gravity is a relationship to mass, and that it's the mass of, or the density, I don't know if mass is even the right word.
You're very close. What I discovered is gravity is a contraction of space. And Einstein told people about it, but I don't know that they ever really caught on. From what I've read, they thought it was not a particularly interesting pathway to follow, although it was direct on, direct hit. He linked gravity to acceleration, which also Newton did. Another one of your boys over there.
Yeah, big occultist as well.
Have come out of England, really.
Yeah.
And Newton discovered that acceleration has something to do with gravity as well, although it's not been highly, talked about, publicized or whatever. But force equals mass times acceleration clearly suggests that somehow we can get mass out of a force that accelerates. If you just do a little simple algebraic twist, you find that you can solve for mass using acceleration and force. Einstein kind of stumbled on the same thing with E equals mc squared, which if you solve for mass, you have an energy in motion. So clearly the link is motion. If you want to get gravity, you need to make electromagnetic particles move in an accelerated fashion. And that's the pathway I followed, thanks to Einstein, who worked that out.
And I suppose we don't notice it in our corporeal forms that we have, but everything is in motion. Our entire solar system is in motion.
Yes.
In the galaxy. Every atom in your body has electrons and whatnot moving. Nothing is static, is it?
You're absolutely right. And that's the key to solving this problem. It's all about motion. Like Einstein said, nothing happens unless something moves.
But you said it wasn't just not motion, but acceleration. Now, how does something continue to accelerate? Because by definition, as far as I can tell, accelerate means it's going faster and faster and faster.
Perfect.
Otherwise, it's decelerating.
You're good thinking. Perfect question. Now we're going to answer that question clearly and leave no doubt that acceleration was the equivalence principle by Einstein was vitally important discovery. So I read, for many years I was searching for, contraction and gravity. They're the same thing, but how does space force to contract? So here we will talk about that right now. In the book from Amir D. Excel, God's Equation, he talks about Einstein's happiest thought. Einstein followed a line of reasoning that began with his happiest thought of his life. Still at the Swiss Patent Office, he conducted one of his famous thought experiments. Einstein imagined a circle spinning in space. The center of the circle did not move, but its circumference was moving quickly in a circular direction. Einstein compared what happens in several reference frames, a standard tool he used in developing the special theory of relativity. He concluded, underline this in your mind, he concluded using his special relativity that the boundary of the disk contracted as it spun. There was a force acting on the circle at the boundary, the centrifugal force, and its action was analogous to that of a gravitational force. But that same contraction that affected the outer circle left the diameter unchanged. Thus, Einstein concluded, in a way that surprised even him, the ratio of the circle to the diameter was no longer pi. He deduced, in the presence of a gravitational force or field, the geometry of space was non-Euclidean. What that means is it was bent. It was bent in a specific way. It was contracted. And where did he get the contraction idea from? Special relativity. When you accelerate any type of charge or mass, it gains mass. As more you accelerate, and you have what Lorentz discovered was a contraction of length in the direction of motion. So that's what Einstein was focusing on, the contraction of length in the direction of motion. So you asked, how do you constantly accelerate? Circular motion is a type of acceleration. Most people don't realize that. They think about acceleration is, and when I get in my car and I hit the gas, I get pushed back. That's linear accelerated motion. But when you go in a circle, an elliptical orbit, you have continuous accelerated motion. And that was the key. When that locked into my head, I said, holy crap, now I know why it was he found the mechanical explanation for the creation of mass, gravity, and what will eventually, as I discovered in my book, lead to the inertial explanation as well, which has been a dark mystery since Newton. You know, how does inertia work? You know, where does that come from? It's from accelerated particles moving in a straight line direction. The faster they move, the more the contraction of the space, and the more it contracts, the more it kind of has a resistance to its acceleration. And that's exactly what we see when we do experiments. It confirms that. All I've done right now is just explain to you the mechanical explanation for how mass, gravity, and inertia work. It's through continuous accelerated motion, or straight line accelerated motion. Both of those create an increase in mass and a contraction of length of that object.
A contraction of length, so it gets squashed.
Yeah,
and this works
for... It makes sense. If you contract something like that, it becomes denser.
Right, yeah. So the relative mass is increased.
So the moving particle, which is a configuration of space, which is typically, not always, a twisted or torsional field, when it moves in that way, it not only contracts, but since it's consubstantial with the space, which means it's made of the same thing, the space that it's made of shrinks in and around that, or contracts in and around that particle. So the motion of those particles through space affects the space. It's an interaction between particles that are in motion and the space that they're in motion inside of. So that's the key breakthrough. Whereas quantum mechanics was always about particle-to-particle interaction. According to Einstein and according to the theory of superrelativity, it never was about that. It was always about a particle-to-space interaction. And the ether is, in fact, real and true, and we need to go back to that, back to the future.
So is the implication of that then that a lot of these sort of tests or ideas are tested in a vacuum? Is the idea then that there's no such thing as a vacuum or empty space?
There's a vacuum in the sense that it doesn't have any atmosphere, but that doesn't mean there's nothing there. And that's a big debate. A lot of scientists, a lot of physicists, a lot of mathematicians really want to stick to a vacuum is a complete void, empty of everything. Yet there's a bunch of scientists that believe in one form of ether or another. The string theorists believe that the space is filled with these fields made of strings. And there's quantum mechanic theorists who believe that there's fields made of all these different, the electron field, the photon field, that are just magically there, and electrons and photons are just excitations of this field. All those are bad models. It's not that complicated. All the particles, all of them, are all electromagnetic. That means they're all transverse waves. And listen to this point. Transverse waves, according to Einstein, who I'm using as authoritative proof, said this: transverse waves only occur in solids. So there's more evidence that space is a solid, a quasi-elastic solid, because all those particles are transverse waves, and that's what they occur in. So there's something out there. So the vacuum isn't really made of nothing. And if you examine that argument, the nothing argument, it doesn't make sense. And I could tell you why quite simply. If space were made of nothing, truly empty, it would not have properties. And space does have measurable properties. Thanks again to James Clerk Maxwell, who discovered that space has two primary properties, permittivity and permeability. And he used those to discover that the speed of light had a specific number. And he came up with the equation, C, the speed of light is equal to 1 over the square root of permittivity times permeability. If space was made of truly nothing, it couldn't have a measurable property of permeability or permittivity, because nothing equals zero all the time. So again, it makes no sense to make those claims. And that's a very common claim that exists in physics and astrophysics now. But there's a group that goes against that, because there's many people that are saying that space is stretching, and it's stretching as it's expanding. And you can't stretch or expand something that does not exist, nor can you, a very simple equation solves this problem once and for all. Distance equals rate times time. If I go into outer space and I'm holding a meter stick and I measure the speed of light going across that meter, it takes a specific finite amount of time to traverse that distance. If that distance was made of nothing, it would have a value of 0. And in that case, the speed of light would be infinitely fast. We never see that. Never. There's only one way to do that. So that means, again, clearly that space that we're measuring across is made of something. It has a density. I don't know how else to say it.
Space was, Mark, if space was completely empty, is it true to say that if something started accelerating in one direction, so linear acceleration, would it continue to accelerate for an infinite amount of time and therefore breach the cosmic speed limit, which is another one of Einstein's notions?
Right.
And it will continue to accelerate forever.
No, you can't do that unless you get into the slipwave, which I talk about in my book. But if we're going to use a standard rocket and test your theory, your model there, you cannot. As you accelerate further and further, it will take more and more energy, according to the special theory of relativity. The more you accelerate, the more energy is required to make you accelerate further. And as you approach the speed of light, the energy it takes to accelerate up to the speed of light becomes infinite. So it would take all the energy of the universe. And so that inertia, you'll have an inertial effect there that's saying, no, the mass is too great. You can't accelerate anymore. That's the special case of special relativity. So
okay.
So
if space was empty, though, completely empty, which we're assuming it isn't because of this these properties that it has. If it was truly empty and a vacuum was absolutely empty, you could use a small amount of acceleration to produce continuous acceleration, because there'd be nothing acting against whatever it is that it's accelerating.
Okay, so you're thinking cleverly. You're thinking, how can
First time for everything.
You need to break the speed of light, right? If you want to go to other planets, you just can't go at the speed of light. It's way too slow. So I said, I'm thinking the same thing as you. I'm working that out. I says, wait a minute. I know aliens. I've worked out the math. There's no way they're using light speed or rockets or anything like that to get here. They got to go fast. Not only do they have to go fast, they got to go tens of thousands of times faster than the speed of light. So yes, you're right. You have to do something to space, which is create a spatial bias drive, which I call the Slipwave spatial bias drive. And when you get inside of this special field, which is simply a gradient magnetic field, you not only cancel gravity, you cancel inertia, you undo the Lorentz transformations that would inhibit you, because what you do, because a magnetic field is a rotation. Now, if you take a little chunk of silly putty and you slap it down on a comic book and you twist it, look what happens to the silly putty as you twist it. It stretches. So what you want to do in order to break the light speed barrier is you have to stretch space, make it thinner, make it less dense. And when you do that, what happens? Permeability and permittivity drop. And in order to go faster, you've got to change those numbers, which are thought to be universal constants. But if you drop a magnetic field into the equation, now you can stretch space. Those two will drop. The density of space will drop. Inertia will be canceled. And you can break the light speed barrier by any number you want. You can travel at the speed of a god. And that's what our alien friends are doing.
Wow.
It's just that simple. And when you gradiate the field, saying one end is very strong in the front of the field, and the other end, you have a really strong, much stronger coil and electrical current going through it. You have a really intense field at the back of the spaceship. Now you have a velocity, which means a motion in a direction, and you can go in any direction, outer space you want. And you can go hellaciously fast. If you want, you can go infinitely fast, which I don't recommend.
No, you get lost.
Yeah,
I mean, how do you? What happens if you like overshoot where you're trying to get to, and you're going 10,000 times the speed of light?
Well,
we're disregarding one major factor here as well, which is time and what happens to time.
Oh yeah, cool. Yeah,
in this scenario.
What's the movie? Was it not McDowell? Matthew McConaughey.
Interstellar.
Yeah, Interstellar, wasn't it?
Yeah, because they talk about if you're traveling faster than the speed of light, you're relative to where you've left, you're going ahead in time, aren't you?
Time is slower.
Yeah.
Yeah, so that must have some pretty big implications.
That's been measured even over really tiny distances, like a clock on a table and a clock on the floor. Would operate at different, because the clock on the table is further away from the center of
field.
Gravity from the Earth. Yeah, the gravitational field, of course.
Gravity slows time. You see, time is a funny thing. It's not really real.
No.
Oh my God! What if you go like, say you've got a 10,000x speed of light drive? All right.
No
okay.
problem.
So what happens? What happens if you go 50 light years in that direction, turn around and come back?
Have
you gone back in time?
No.
Damn it!
No.
But
That only works when you use rockets or some external force to push your ship along. Then all of the things of special relativity are in play. Once you get into the side, the slipwave, which is a inverse hyperbolic field, it's an anti-gravity field. Once you're inside of this, you're disconnecting from the Lorentz transformations. They no longer apply because the thing that you're moving through has been altered. It's been thinned out. And so what happens when you get inside the slipwave, which is an anti-gravity field, the zero gravity field, whatever, time actually goes a little bit faster. So now you get, once you're in the slipwave, you're in absolute time that Newton used to talk about. Well, it turns out, in this case, Newton was right. There is an absolute time flow. and that time flow. If you were to go into outer space and, cancel all the motions of the Earth, of the solar system, of its rotation, and you would go to absolutely zero relative to all those motions, and you looked at your clock, it would be running faster than the clock on Earth. Very slightly, but it would be running faster. The same thing happens when you get inside the slipwave. So now time becomes absolute. So you're going 50,000 times the speed of light, which if you're not in a slipwave is extremely fatal. Oh yeah, you got to be,
you need a chap in front waving a red flag to make sure everyone gets out of the way.
Light is incredibly dangerous. You better know what you're doing, and you better not have any technical difficulties, because you won't have time to fix anything if you lose the slipwave. If you lose that field integrity at 50,000 times the speed of light, all the Lorentz contraction things kick in, the time dilation, all of it, and you turn into, if you're lucky, a little tiny black hole. So you need to maintain that field integrity the whole time you're traveling at or beyond the speed of light. So the time problem is not a problem either, because you escape the time dilation issue because you're biasing the space. You're changing the rules for special relativity. So really, special relativity is a special case that needs to be, those equations need to be extended. And I will work with somebody to help them do that. If they acknowledge my theory is correct, I know how to solve that problem too. But that's going to take some work. But your question is a good question. The beauty is, and you need to travel, if you're going to do interstellar travel, it's not convenient for you to go out and back in, let's say, an hour, travel to a far distant place at 50,000 times the speed of light, and find that when you get back, 150 years has gone by on planet Earth. This is not practical. This is not a tolerable situation. And this species of the human will, we don't live 150 years. So we need to get where we're going in a hurry. That means if I got to go to Proxima Centauri, which is 4.2 light years away, I better be able to do it in 15, 20 minutes, an hour. I know this sounds absurd, but believe me, it's very, very possible. Doable.
A lot of science sounded absurd the first time it was talked about. So
yeah, we've mentioned Giordano Bruno a few times over the last few weeks, haven't we?
Yeah.
Something you've mentioned a couple of times is this what's it? The Lorentz
transformations.
What are they? I've not heard that term before.
They're a set of equations that Einstein discovered along with Lorentz, and there was another mathematician in Europe. What was his name? I don't want to say it correctly. It's French. Poincaré. And these guys came up with this set of equations, which were based on ether theory. So these equations work out right. They test out beautifully. And all of them describe what happens to you when you move at this near the speed of light. Time dilation, time slows down. It's not time that's slowing down. Time can't be affected. It's not real. What's slowing down is the clocks that measure the time. That's it. It's just that simple. So the particles inside of the clocks can't move because all of their motion is being focused on the acceleration forward. So as they're spinning around in this form, let's say we're looking at inside a neutron or a proton. We go to here. The toroidal, or this motion is a trefoil knot. That's what I predicted is the motion that's inside of both a neutron and a proton. When you're moving at the speed of light and you're not in a slipwave, those things flatten out because they're spherical. They'll flatten out and they'll slow down every time they try to move in the forward direction. Eventually, what you'll have is a non-functioning system. You can't move. You won't be able to move forward. Your clocks won't be able to move. All of this is real. It's physical and it's mechanical. And without shielding from the Lorentz transformations, we can't break the light speed barrier. We have time problems, as you mentioned. We have physical problems, basically, and we can't generate enough energy to go fast enough to break the light speed barrier. But all of this is overcome when we use the slipwave, which I talk about in my book extensively.
Mark, isn't it incredibly dangerous? You briefly mentioned that if a
black hole.
Yeah, you briefly mentioned that if one of these anti-gravity fields were to collapse, one of the best case scenarios would be a small black hole. How, knowing as we are humans and what humans do, wouldn't the first thing that someone would be thinking of, and I might be the first person to have thought of it, but I'm human, so I'll take that on the chin for us. But one of the first things we would think about would be to intentionally collapse one of these fields and create some sort of weapon.
Yeah, there's always people who want to create weapons. And
how would that be prevented?
It could be a hellacious weapon, because you could fire. Let's say you made a spaceship the size of a basketball, and you accelerated it to let's say just 10 times the speed of light. That's fine. And you shoot it You shoot it at the sun. You get it up to 10 times the speed of light, and then without slowing it down, which is what you're supposed to do when you're traveling in the slipwave, without slowing it down, you just cut the field off. So now all of a sudden that basketball flattens into a pancake and then shrinks to a dot, basically, and it has enormous mass, maybe more mass than the sun and the whole solar system altogether. I don't know, because it will slow down to just slightly below the speed of light. And that thing will be making its way toward the sun, which has inside of it something I'm going to announce here tonight on this show. The sun has a solid neutronium core. This is going to eventually be proven. It's part of my cosmology theory about how the stars are formed. It's the only sensible explanation. So what is going on inside of the sun? We have a neutronium sphere, which is nothing but solid neutrons packed together very tightly. That's what black holes are made of. They're just packed even tighter. So if you were to hit the sun square on with this, there would be a massive explosion. The sun would be gone. I don't know what would be left, but it would end everything for everyone. It's incredibly dangerous, and you have to.
And that's just one nut job with a basketball. I mean,
yeah. I try not to think about weapons. I try to think about practical uses and applications that will benefit humanity. Why anybody would want to do that, I don't know. But
Ben, you may have unintentionally solved Fermi's paradox there.
Yeah.
The reason why, it's one of the arguments for the people who don't believe in ET or aliens is they talk about Fermi's paradox, and if there was aliens all over the galaxy, they would be here and blah 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 blah. And so that could be one argument in favor.
Yeah, just tossing basketballs around.
Yeah, as soon as you get a basketball at light speed, you end up destroying yourself.
Well,
do you know it raises a good point, because technology like this, which is so dangerous, requires humanity to have a certain level of maturity.
Yeah,
and
which we don't have.
We're nowhere near. We're nowhere near that.
Well, something must be right, because if we weren't ready for this, I wouldn't have come up for this. I believe in intelligent design, and nothing is accidental in this universe. Spiritually speaking, physically speaking, everything has a cause and an effect, and everything is by plan. Yes, we still have free will and choice, but we're executing plans. We call those plan execution our lives. And I wouldn't be here with this information now if we weren't ready and it wasn't necessary. That's the other problem that may be out there lingering that we don't know about.
What if the plan though is to 3-pointer the sun, and that's part of the plan to destroy?
No, it's never a plan to destroy. That's where humans get involved with things that break. That's part of being a human, is to make mistakes. That would be a big mistake.
Yeah.
But you know what? Nobody dies. Humans, all spirit beings, we're all eternal. Yeah, we could be wiped out. We would just go back to the other side from whence we came from. And there would be a new planet created. It's probably already being formed. And at some point, we'll have to leave this planet. And that's one of the main motivations for this, is that we never know when the end is coming. And it doesn't have to be by some mistake we do. It could be somebody out there pushes an asteroid at us and decides we need to not be around, we're a threat or whatever. And all it needs is maybe a 10-mile wide asteroid, hits the mantle, cracks it open, which will find that the Earth's core is extremely unstable already, won't survive that. Nobody will survive. It'll be a species-ending event. There will be not even bacteria left after that. So if that's always a threat. The only way
Keith Richards might survive.
Yeah, the only way to dodge that threat is not be there when it happens. And the way that has to happen is we need to have faster than light space travel. We need to have interstellar starships. We need colonies somewhere else, just in case something here goes wrong. So I'm pushing hard for anti-gravity, and I'm going to continue to push hard for anti-gravity because I know it's real. I know it's true, and we need to get work on it. And that way we need to do the experiments in my book about magnetism, prove that we can create an anti-gravity field, and then start learning how to build starships.
Mark, do you think one thing that strikes me, let's assume that we can get the practical side done, so like the anti-gravity drive, if you want to call it, I can't remember what term you used. So we can use this to create this velocity. It seems to me that one of the main things you're going to need is an insane amount of computing power for navigation and whatnot. Do you think we're far off being able to do that?
I think it's not so much the computing power that's the problem. It's the sensing system, the sensory system, that you're going faster than the speed of light. Radar isn't going to work. You're going to overtake the photons that you're trying to shoot out. So you have to kind of pre-map with a very smart computer system, very powerful, but we've made some really Jim Dandy powerful computing systems. And what we're processing was you're going to have a star map like you have on your car. You have the map installed. You're going to have a star map of the galaxy. And you're going to have it all saved in 3D and, relative positions of all the stars. And you're going to have to know your position. And the best thing you could do is shoot a probe out ahead of you with radar, and which is what I would recommend. And then maybe be able to beam back from the probe that's moving ahead of you at the same speed information about, is there anything out there? Did you hit anything? Whatever, to avoid collisions. But fortunately, space is really, really empty. So long as you exit the solar system the proper way, you don't go along the plane of the ecliptic, because that's where all the planets are, all the asteroids. You want to go, this is the plane of the ecliptic here, where all the planets are going around the sun. You want to go straight up and then away. So you avoid all that clutter safely, and then, at sub-light speed or whatever, and then take off from that point.
Two questions I have, Mark. One is, how do you slow down? And the second one is related to the Slipwave spatial bias drive. Are you creating a bubble, this anti-gravitational field that contains, that is almost outside space, or it bends space around? Will it also bend any matter also? And therefore you could just go in a straight line and fly through planets and through star systems and whatnot?
Bending space in that way would take a strong, folding space up and taking a shortcut would take an immensely powerful gravitational field. It's not efficient. We don't have enough energy to do that, and you would die.
But is it outside of space, quote unquote, outside of the soup?
No.
This
no, it is
field.
A bubble, but the bubble.
So it could hit anything, any matter within space. You're at risk of hitting.
Yes. Yeah, you're at risk of hitting matter, but because you're using a magnetic field, much like how the Earth does with the solar wind and all the stuff coming from the sun, you see how it bends the particles and puts them around the pole? Well, this magnetic field is super strong. So incoming particles are gonna, if you're going through space like this, they're going around you and out.
Right.
And that's why the UFOs do not make sonic booms, because the air around within that magnetic field that's very close to the UFO is rarefied, almost to the point of a vacuum. So they slip through the air, water, whatever, it's no problem. And that's what we see. That's exactly what we see. So I just
you couldn't do that through a solid.
Why?
Could you do that through a solid though? And if not, why?
Now
not?
We're going to Buckaroo Banzai.
I'm just thinking, because you could feasibly, I suppose, go through the outer limits of a star. It's gaseous.
Yeah.
You've mentioned water is no problem.
Right.
So at what point does it become a problem?
You got to remember
crystalline structures, or
when they're not going through water at the speed of light, though, or faster than light.
No,
they're going at 500 miles an hour.
Right.
There's a big difference between there's where the mass relationship and everything comes in.
Right. Okay. So could you go through a planet slower? I don't know. I'm just thinking. I'm thinking about the. It's almost related to my first question. Like, how do you slow down? And I imagine you would only accelerate for a fraction of a second inside this field.
Well, to slow down, I'll answer that question first because I want to deal with that very quickly. You have a gradient field where the weak end of the field is at the front and the strong end is at the back. And you have to know, when you're out of space and you have a zero gravity field already, to you, it feels like you're not moving at all. The only way you know is if you look at something else and you look at that light. It's going to be compressed to the point of blackness. And so you'll need a sensing system that will take the incoming photons, which are going to be compressed to such extreme levels, they'll be like in the terahertz region or beyond that. And you have to have a sensor that can interpret they're there, you're moving. Therefore, the star you're heading toward, you're moving at 50,000 times the speed of light. So now you have to make that you have to decompress the Doppler effect there. And when you do that, when the star appears normal again without any Doppler effect, which is a contraction, a compression in the motion, in the direction of motion. When it goes back to normal light, you've stopped, because now you're not moving hardly at all relative to that star that you were moving toward. Now it's safe to shut off the field. And how you do that is you simply reverse the power. You put the high power up front and the lower power in the back, but you never, ever eliminate the field. You never shut it all the way off. Oh, that would be fatal. And that's where you need some good computing power, and you better control your currents properly. It's direct current flow. So you have to just shift the amount of energy coming in the front coils and shift the amount of energy and you could do it like that. It could be instantaneous. And you just swap them and then you'll stop. And it seems like you would be smashed into the front of the ship, but you feel nothing. There's no inertia. Well, as long as you maintain that field. Then when you have stopped, really stopped the absolute motion, then you can drop the field and you'll feel nothing. It'll say, well, okay, I don't feel anything. It's stopped and everything's fine. But you have to do it in that sequence. If you don't, it's fatal. And I'm sure the people of Earth who already have made these spaceships, probably United States, have suffered casualties along the way from inertial leakage. Any incomplete field shape, any part of that craft that isn't protected from inertia, and there's an occupant, when they do high-speed maneuvers, they'll be killed. You have to be in that field entirely. Inertia has to completely be canceled to be safe. Then you can go 50,000 miles an hour this way and turn 90 degrees and not feel a thing. It's as if you were in nothing at all. You'll be floating in the middle of the ship or strapped down in your chair. You won't feel a thing unless you look out the window and see it, which I'm sure will make you not feel good. So I reckon.
How practical is it to travel at sublight speed in these things? So how is it possible to travel down to sort of walking pace, for instance? Because you would have to come to a stop if you were going to use
land.
This for traveling. Yeah, to land, yeah.
I talk about making a supercar, which is, a car that it floats. It's just like the ones in Star Wars or whatever, or the shuttlecraft, where you can go in the atmosphere. And I talk about, hey, you could have one of these cars with a GPS system and all that, the auto nav, which they're now developing just in time for the use with this. And you could set this thing up, program it, go up 1,000 feet, go 50,000 miles an hour, which will get you from where I live to Tahiti in less than 15 minutes. And wouldn't that be nice to have a breakfast on the beach in Tahiti, maybe have a little lunch over there, and then you get a little groggy in the afternoon and you're back home in your bed in less than 15 minutes. Or
maybe check out the pyramids at dinner time.
You can check out the pyramids. You can go, like I said, you can go have breakfast in France, have lunch in Rome, and be back for your nap at 3 in the afternoon, no problem. This could be the new reality, the new world, as long as we do what I say in the book, prove that magnetism cancels gravity. That's the first step. And then
would you even need a craft? I'm just thinking about how to generate thrust now. I'm designing in my head already. But would you, if you were to generate a field, then you have a field, which is great. But how do you move that forward? Wouldn't your initial thrust generation have to be outside, if indeed you need that thrust? And if you don't, do you need a craft at all? Could you just have like a wristwatch, like an app or something? And then
the thrust comes from the shape of the space. I use in my book an example, a bubble in the bottom of the ocean in water. How does it move forward? It's a perfect example. There's a gradient field of pressure. Pressure is the way for movement. If you think about, you want thrust, well, then you better use pressure gradients, pressure difference. Water in a hose moves because of pressure difference. The winds blow because of high and low pressure systems. Your cars move because of compressions in the pistons. Everywhere you look for examples, if you want to see how things move, they're using pressure differences. Inside a particle, they use a pressure difference. The slipwave creates a pressure difference within the field itself. That's why I call it the slipwave. It slips through space because it's being pushed at the rear end and allowed to go forward, because the space within the slipwave field created by magnetism, it pulls space apart. You create a bubble of very low density space, and you create a bigger bubble at the end, the back end. So the space around it that's normal is pushing on your spacecraft, pushing on that field. And that's what makes it go. And that field is able to move effortlessly because everything within it is shielded from gravity, is shielded from inertia. There's no resistance. So it's a beautiful, sensible, perfectly working system. And if you don't believe me, ask the UFO guys that are using it now to fly all over the universe. It's the only logical, reasonable explanation. They're using this technology. And so it's a good question. That's how you get the propulsion. It's magnetic propulsion. And they knew that even way back in the 50s, early 40s, mid 40s, early 50s. I found a reference in a book written by J.K. Jessup, who was found dead in a hotel room. They said he hung himself, but I'm not sure. One of the first guys to write a UFO book, and he says in that book, he says he's making a kind of a funny comment from the Air Force. We don't need magnetic fields. We don't need that. We were going to use jets and rockets. And everywhere on the internet, you go to that sentence, they blank out the word magnetic. And they just leave the M, and there's just a gap. It's in my book. I show you that introduction section in the book that he wrote about UFOs. Somebody went all through the internet, removed the word magnetically, and just left the M for some reason. So only person would know it was somebody that knows that magnetic fields are what's used to propel UFOs. I mean, the evidence is there.
Mark, the sort of the traditional rocketry organizations across the world, like NASA and the European Space Agency, that the guys who are sending up satellites and International Space Station and all this. Do you think they're aware of this, or have they been kept out of the loop?
Well, you see some astronauts talk about like they know about something's going on. You see references to the Clintons and whatever and the ex-presidents. They won't come right out and say anything. They kind of very gingerly step around the UFO topic. I'm sure that the higher ups in NSA and CIA and probably the FBI, to contain people who know the truth, have come to know about this situation. So we got an odd situation here where only a very select elite group of people in the world know about this. They're keeping it quiet. And why are they keeping it quiet? Because anti-gravity technology and faster than light motion gives a strategic military advantage to the people who have it. Mm-hmm. It's just that simple. It's not even worrying about, will there be a world panic? Maybe somebody will get upset. I don't know. But if they're not attacking, there's no reason to be upset. And really, the big reason is, hey, they tried to keep the atom bomb secret. They weren't so good about that. But maybe they've learned their lesson there, and they've learned to discredit people who talk about this stuff. And disinformation has been a very effective tool to keep this out of the news, to keep this realization from the people, I'm sure. I think you guys are well aware of that. And the motivations are very simple. They want to keep that power to themselves.
Power. Yeah. Yeah.
Sooner or later, Mark, if we don't advance, we'll all be gone. Something's going to go wrong and we're not going to be able to handle it.
Yeah. Absolutely.
Well, Mark, on that note, I can't believe we've done over an hour already, and I could go on talking to you all night about, we haven't touched on disclosure or, the nature of why we're here, what's our purpose in life. So, but it's been fascinating to talk to you. I've really enjoyed it.
Yeah.
Where should people go if they want to find out more?
I have a website, www.super-relativity.com. And on the front page, there's a link to get my book on Amazon, or you could order one from my website, and I'll sign it and send it to you. So that's the two ways doing it right now. And hopefully people come out there. I got some very interesting articles that they could read in my blog. I got other shows that they could watch. I'd like to upload this to my blog if that's okay with you guys. I don't know.
Yeah, of course. Sure.
Okay. This is all part of my task now. I need to get this information out there so people can take action and help make this a better world. I hope a utopian world, a dream world, where traveling to other planets and talking to other aliens from other worlds will become a commonplace thing. Like 150 years ago, nobody ever dreamed that we'd be in flying airplanes and having cars. And now that's normal. I'm talking about changing what's normal and changing it for the better.
The new normal, you might say.
The new normal.
Yeah. Well, fantastic. I'll put all the links in the description, so please do check out Mark's website, super-relativity.com, and check out the book. And thanks once again for joining us. Just stay on the line for us for 1 minute, Mark, while we play ourselves out. And we'll catch you on the flip side.